All right, so we ended last class with the plum pudding model, and now we're going forward from there. And maybe. So Ernest Rutherford, who worked with J.J. Thomson on the plum pudding model, wanted to test it further. He did believe in the plum pudding model. He thought it was a real thing. And so he did some additional experiments to prove the validity of Rutherford and the plum pudding model. Or not Rutherford and the plum pudding, Thomson and the plum pudding model. So Rutherford did a gold foil experiment, and he took a thin sheet of gold foil and he fired alpha particles. Alpha particles have a positive charge at the gold foil. And his belief was that they should all just fly right through. There should be no issue, because the plum pudding model kind of believed there was a generic positive cloud. And so those alpha particles should pass through that positive cloud with no resistance whatsoever. There was no substance to that positivity. All the real substance was in the negative electrons. So he fired his alpha particles, and the vast majority went straight through. It was no big deal. However, he did notice, because he used this detector ring, he noticed flashes at fairly wide angles, like it was skipping off of something. And he even had a few flashes coming backwards out of the gold foil, which implied that not only was there something very dense or solid in there that they weren't able to pass through, but that this had to have a positive charge, because if it was a big chunk of negativity, they would stick. Opposite charges attract, and they were reflecting backwards. So from this, he created a new model, and this new model is the modern version, and I'm going to skip over to it right now. You can see the vast majority of alpha particles going through the plum pudding model, which was the predicted result, but the actual result was different, and these deflections implied there was something very, very heavy relatively, very, very dense and solid, and had a positive charge. And so from this, Rutherford created a variation on the atomic model, which included a nucleus. So he proposed the nuclear theory of the atom. And the nuclear theory has three basic parts. Most of the atom's mass and all of its charge are contained in the small core of the nucleus. And most of the volume is actually empty space that has some negatively charged electrons scattered throughout it. To give you a scale, if we went out to the football field and we put like a marble in the middle of the football field, that would be our nucleus. And the top of the bleachers actually would be the outer edge of where the electrons are located. And the electrons would be like the period at the end of a sentence, not the big periods used on this PowerPoint, but like little periods in a book. Most of the volume of the atom is empty space. So they're kind of non-existent, which is really weird because they're really solid. There are many negatively charged electrons outside the nucleus, and they are pulled in by the positive charges, which are called protons. And when Rutherford first proposed this, he didn't have the neutrons. So all of his mass was in the protons at that point. So later work by Rutherford and one of his students, James Chadwick, ultimately demonstrated there was more mass than the protons accounted for. And this was due to another particle, which were called the neutrons, and they are neutral particles within the nucleus. Much like this Swiss village, Switzerland is neutral, so are neutrons. The mass of a neutron is the same as a proton, more or less. It has no electrical charge, so it's not positive or negative. And thus helium, which has 2 protons, but has 4 times the mass of hydrogen, and this is kind of where they kind of had their aha moment, obviously has 2 more things that contain mass. But since there's only 2 protons and 2 electrons, it can't have a charge, so it has 2 neutrons. Hydrogen is actually pretty unique in the fact that it has no neutrons at all, typically. There are a few versions of hydrogen that do have some neutrons, but the normal hydrogen atom that you would find floating around the room doesn't have one. So all atoms are composed of the same basic subatomic particles: protons, neutrons, electrons. Protons and neutrons are in the nucleus while electrons are outside. And that's the basics. I mean, that's pretty standard. We learned all that last year. If you're a little fuzzy still, there is a video. I'm not going to show you the video. You can go watch the video. This PowerPoint is uploaded to Teams in the files. So the charge of the proton and the electron are equal in magnitude, but opposite in sign. So if you look, and hopefully my mouse pointer shows up, protons +1, electrons -1, equal but opposite in sign. And if we want to look at exact charges, they are there in coulombs, but I don't care. +1, -1, that's what we're really looking at. You'll notice mass of 1, because we're going to round that off a little bit, YOLO. And the electron has no mass, even easier. The most important number in terms of an atom and helping us identify the atom is the number of protons in its nucleus. This is known as the Z number, and it is the atomic number. The atomic number is the number of protons, and it is designated Z. Remember this Z because it's going to come up in some later topics we are covering. Also, the mass number is the protons and the neutrons added together. So we have our protons, we have our neutrons, we put them together to get our mass number. Typically, we are given the mass number and the atomic number, and we actually have to use that to find our neutrons. That's much, much more common. Each element is identified by a unique atomic number. So in my bacon compound here, I have 56 for barium, 27 for cobalt, and 7 for nitrogen. That is their atomic number, which again, to remind us, is our number of protons. So barium has 56 protons, cobalt has 27, and nitrogen has 7 protons. Side note, since they're probably neutral, they have no charge, that means if, say, barium has 56 protons, it should have 56 electrons so that it is neutral, should be neutral. They also have a unique chemical symbol. First letter is always capitalized. That's how we have a new symbol. Some symbols have only one letter. Other symbols have a letter and a smaller lowercase letter. So it's a 2-letter combo, but it'll always be capital, lowercase, capital, lowercase. If you have 2 capitals side by side, that's actually 2 different elements. All atoms of a given element have the same number of protons. It's not going to change. So all carbons have 6 protons. That's what makes them carbon. All neons have 10 protons. That's what makes them neon. However, they don't necessarily have the same number of neutrons. And the more neutrons you have, the heavier you are. So neon has 10 protons, and most neon, ironically enough, has 10 neutrons. But sometimes they have 11. These are slightly thick neons. And when they get all the way up to 12, we're talking thick with 2 C's. Those are our heavyweight neon atoms. Atoms of the same number of protons but a different number of neutrons are called isotopes. So when we look at neon, if we see a mass of 20 and then a mass of 21, they're isotopes. They're both neon. They chemically behave the same. They will bind in the same ratios. They'll end up in the same compounds. But one of them's a little heavier. The relative amount of each isotope is measured scientifically. They naturally occur and it's fairly constant. So if I were to take a neon sample from, say, here in Reno and another neon sample from, say, Switzerland, they should have the same percentage of each isotope or extremely close. These are called the natural abundance of the isotopes, and we've advanced a lot in our measurement of these, and our values are getting pretty tight. So if you look at periodic tables, say one made in 2000 and one made in 2020, you would find maybe some changes in the mass of the elements, but that has to do with the changes in these isotopes. So the percent composition. The sum of the neutrons and the protons, again, is our mass number. Our mass number is technically designated by the symbol A. So when you see an A, it's the mass number. Z is our atomic number. And you can see that depicted right here in this notation. So A is our protons plus our neutrons. Z is just our protons. And then we give a chemical symbol. This is a notation for showing different isotopes, and you can see it depicted here with neon. So again, standard neon, a little bit thick, 2 C's thick. This just helps us designate the different isotopes we're looking at. As we look at these, there's a second notation we'll use that's fairly common, and here we go. Here's neon. Ne20, Ne21, and Ne22. So we're only giving the mass number. We've dropped that atomic number. We don't really need the atomic number because we can find that very quickly from the symbol in a periodic table. And there's periodic tables all over the world. There's like 4 in my classroom right now. I think there's one somewhere above me. Yep, you can see one above me right now. I mean, they're everywhere. As it turns out, though, be aware, some of these isotopes are not stable and they are radioactive. So that is also important to designate which isotope. There are pure samples of isotopes. For example, I have a friend who buys, instead of tanks of hydrogen gas, he'll actually buy a tank of deuterium, which is a hydrogen isotope that actually has 1 electron. Therefore, those hydrogen atoms have a mass of 2 AMUs instead of just 1 AMU. So here are both notations. I lost my mouse. Oh man, what'd I do? Here are both notations depicted. Again, they all have 10 protons because that is what makes them neon. They do have different numbers of neutrons, which by default gives them different masses. And the percent abundance. So once again, neon 20 is the most common. 90% of the neon in the world is neon 20. 9.25% is neon 22. And then the exceedingly rare one is neon 21. Sorry for yawning. The number of electrons in a neutral atom is typically equal to the proton, so Z. But a lot of times in a chemical change, what drives the reaction is moving electrons from one atom to another, or sharing, or trading, or shuffling. These share, trade, shuffles, if they flat out give or take electrons, so they're trading at this point, kind of like Pokemon cards when we were 5. Well, when you were 5, I was like old. I'm always old. If we give away electrons, we gave away our negativity, that makes us positive. And so positively charged ions are called cations. And you can see there's a cat next to the cations. That looks a lot like my cat Gus. It's super cute. It makes me happy. And then the negatively charged ions are called anions. The other thing you can look for is cations have a positive, a little plus sign in the T built into their name to help us remember they are positive. Here are some elements that make predictable positive and predictable negative charges. These are very consistent, kind of something you should memorize for the most part. You can pause it and write them down or look at them or study them if you would like. Come on. Did I go like 2 slides here? No, I only want 1. Okay, cool. So going back to our isotopes here, we have a mass number and we have a percent abundance. How do we figure out the mass of neon for the periodic table? That's an average atomic mass. And that average atomic mass is calculated by taking the fraction of the isotope. So a fraction is the percent in decimal form. So 90% would be 0.90, that's the fraction. So the only difference between the fraction and the percentage is you multiply by 100. And then you multiply it by the mass of that isotope. When we're doing these average atomic masses, we're actually not going to use the mass number, because if you recall back a bunch of slides, the mass of a proton, the mass of a neutron, were really, really close, but there was a little difference out, like I think the 10,000th decimal place. And then I said electrons are 0, but if you go 10,000ths over, you'll actually find a little bit of mass there. And so we got to account for those decimals. And so we use a more accurate mass of each isotope. So you would take the fraction of the isotope times its mass. The fraction of the next isotope times the mass of that isotope, fraction of the next isotope times the mass of that isotope, so on and so forth. So if there's 5 isotopes, you'll do this 5 times. If there's only 2, we'll only do the first 2. It's not a big deal. So chlorine occurs in 2 primary forms. Chlorine 35, which has a real mass of 34.97. So you can kind of see they rounded to 35. and chlorine 37, which is really 36.97. Again, we rounded. Chlorine 35 makes up 3/4 of the chlorine in the world, and chlorine 37 makes up 1/4, give or take rounding. So how do we go back? So if we look at this, the fraction times the mass plus the fraction times the mass. So here we go. Our fraction, 24.23%, becomes 0.2423. We divided by 100 times its mass, 36.97, and we get 8.9578. And then our 3/4, 0.7577 times our 34.97 gives us our 26.4968. We then add those two values together to get our actual average atomic mass. Now, if you're not sure, there's a little video down here. I would make it full size. I wouldn't try and watch that tiny little screen. That's just insane. There should be a way to, there you go. You can copy the video URL and open it in another window by right-clicking. I had to figure out which hand's which on your mouse. So let me come over here, tap out of that, and go to the next slide. So those are atoms. That's how we find the parts, protons, neutrons, electrons. That's how we find our mass. That's kind of all review. Now we got to name them. So ionic compounds kind of come in two primary types. Metal forms with only one charge and metal forms with two or more charges or more than one charge. So the very first thing we're going to do is figure out, do we have a type 1 or do we have a type 2? Type 1s are, again, those positive charges we wrote down earlier. Couple charges to memorize because they come up often enough. Zinc is always +2 and silver is always +1. So kind of in the back of your head, try and store that information. Great news, they don't usually put it on the AP exam where you have to like recall all of this amazing information, but just kind of, it's good to know. And come on, you're not gonna go forward. All right. Common monoatomic anions, so our negatives. So we looked at our cations, now we're looking at some anions. We have fluorine, chlorine, bromine, iodine, oxygen, sulfur, nitrogen, and phosphorus. However, when they are anions, the name actually becomes, we take the fluor, the base, take off the INE, and we put ide. Fluoride, chloride, bromide, iodide, oxide, sulfide, nitride, and phosphide. These three kind of in the back of your mind, retain them a little bit because they're going to come back in a little while in a slightly different form, and we need to be able to tell the two apart. So type 1, there's only one charge on our cation. We're going to use our binary compounds, and it basically contains two elements. You name the metal, and then you name the anion with an IDE ending. It contains two different elements, but not necessarily two atoms. For example, if we were to look at this, oh, come on, come back up here. What happens when I do that? No, that's not what I want. No. Oh, that's what I want. All right. So, I'm sorry. I will get better at the tech eventually. So, for example, Na2, make that more A-like. Na2O, when we name it, we would name our cation, sodium, and then we would name our anion, which is oxygen, but again, because it is the anion, it becomes oxide. Now, there are 3 atoms present, but there are only 2 elements. That's the only thing I really wanted to clarify in that as we kind of went over it, because that could become a big factor if you start to confuse yourself. Moving on, maybe. The second type of compound contains a metal that has more than one charge. So we got to tell people which charge it's using that time. It's kind of like split personalities, like what mood are they in today? So that kind of ends up being kind of important. Iron, for instance, has 2 pretty common forms, 2+ and 3+. And most of these are going to be transition metals. So when we look at the periodic table, we're talking that D block when we did our blocks on the periodic table last year. So iron in this first compound has a charge of +2. How do I know it's +2? Whereas here it is +3. How do we know what the charge is? We're typically going to be working backwards to figure these out, and we're going to get to that. So once we figured out what it is, so here it's iron and sulfur. We'll do this first one with the +2 charge. We're going to look at this one first. The name of the metal, again, iron, very simple. The charge in Roman numerals, so a Roman numeral 2. And then the base, and that was sulfur, so sulfide. So that would be iron 2 sulfide. The Roman numeral tells me what the charge is on my metal. So here's a list of some common ones. This is an older naming system. We don't use it anymore. But what they would do is add OUS for the smaller charge and IC for the larger charge. So chromis, chromic, ferrous, ferric, and that's using the original Latin iron name, so on and so forth. Those were really confusing and complicated because cuprous is +1, whereas ferrous, also OUS, is +2. So you had to kind of memorize all that. Whereas copper 1 means it's +1. I don't have to think at all. It's a miracle. So how do we figure out those charges? We work backwards. So here's a compound, CrBr3. And we want to determine the charge on the chromium. And so it says here, the total charge on the cation and total charge on the anion have to equal 0. Otherwise, it's not neutral and bad things are going to happen. Chromium charge plus 3 of the bromium charge has to equal 0. So they're doing kind of a little bit of algebra. Because bromium doesn't change, it only ever has 1 charge, and we look at the periodic table, it's in column 17, and in column 17, everything has a -1 charge. But we have 3 of them. So 3 times -1 is -3. So what is chromium charge? X minus 3 equals 0. It has to be +3. Therefore, we can figure out. So you can set them up like little algebra problems if you want. We talked about crisscross last year. You can anti-crisscross. There's a few options on this. Polyatomic ions are another factor that comes up. You memorized them, or you had them on your handy dandy last year. For example, sodium NO2 is sodium for Na. And then NO2 is a polyatomic ion by the name of nitrite, ITE. And so that's sodium nitrite. They name the exact same way. The only difference is the anions are more than 1 atom. And their name is what the name is. There's no changing the endings on those. They have names and they're set. We don't mess with them. So pretty simple. We don't have to change much there. Here's a list of polyatomic ions. Again, on the AP exam, they're not going to do a lot of naming type stuff on you, but they might tell you you have a compound containing potassium chlorate. And you need to know this well enough to pick the formula out of the balanced equation they gave you. So you kind of got to know them. In my opinion, it is absolutely worth memorizing them so you know them, and it makes things so much faster and easier for you. The debate on the AP forums, half the teachers make kids memorize them, the other half don't, because it's not something that should impede your ability to be successful on the AP exam. But it will help you read the backs of bottles and stuff. Most polyatomic ions are oxyanions, meaning it's something connected to oxygen. So here's nitrogen connected to oxygen. Here's sulfur connected to oxygen. A lot of times there's 2 in the series. One has more oxygen than the other. I really wish I'd grouped these differently on the slide. So it was the NO3, NO2, then the SO4, SO3. The one with more oxygen, in this case 3 and 4, always gets an ATE ending, nitrate, sulfate. And the one with less oxygen gets an ite. Again, it's not consistent, 3 and 4 versus for the 8s, 2 and 3 for the ites. It has to do with what's common for that element. My recommendation for these, memorize all the 8s. Don't worry about the ites because you know the ites just have one less. So if you know nitrate is NO3 and something mentions nitrite, take one oxygen off, you're good to go. Some of them have bigger groups. Again, memorize all the eights because if you know all of your ATEs, chlorate, one smaller, one less oxygen, so 3 to 2 is chlorite. If you take another oxygen off, you put a hypo in front of your chlorite. If you put an oxygen on, you put a per in front of your 8. Pretty simple. Hypochlorite, chlorite, chlorate, perchlorate, hypobromite, bromite, bromate, perbromate. You're adding a prefix to add, you know, it gives you a little more range to run into. Notice the charges are all the same. These are all -1, all -1. Adding or taking away oxygen does not change the charge of our polyatomic ions. And then we get to hydrating, and that's another lesson. So I'm going to stop here. So you only have to watch this much. That's it. If you have questions, you can rewind. You can get a hold of me. You should know how to do that. And we'll go from there. Have a wonderful day. And we will hopefully get all this stuff sorted out.